Yeah, down arrow we could call F sub G. Very good. Okay, for force of gravity. Now, what do we call the force of gravity? What's our? Yeah, it's just weight, isn't it? Good. What about the up arrow? Yeah, F sub T. What's that stand for?
Tension.
Tension. Yeah, good. Tension. Tension is a word we use to describe force that's transmitted through something flexible, like a rope or a string or a cable. Okay, very good. All right, good job, good job. Okay, good. So notice that characteristic of any free body diagram, all of the forces are originating at the point that represents the object, right? Good job. Okay, we're gonna do a little experiment, just a little demonstration. Nothing too major, don't get your hopes up. Nothing too horribly exciting here. All I'm gonna do, I think we maybe, did I introduce you to this yesterday? Maybe we just started talking about this. So this is a spring scale, glorified rubber band. All it does is as it stretches, it applies a return force. The greater the force or the more it's stretched, just like a rubber band. Only it's got a scale on it. So I can quantify the amount of force, the amount of tension that's acting through this rubber band, okay? So I'm going to take this friction block and I'm gonna put it on its smooth side. There's a smooth side and a rough side. So I'm gonna put it on the smooth side and I'm gonna put on I don't want quite that much. It wasn't quite enough last time. I'm gonna put on a 100 gram mass, I'm gonna add that. And I'm gonna pull with a certain force. Okay, I'm gonna pull with 1 Newton of force. Now watch what happens when I do that. What happened? We'll do it again? Yeah, it accelerated, didn't it? Everybody agree? I'll do it one more time. Okay, I'll get it up to 100 and then I'll let go. Okay, agree? Okay, so let's draw that free body diagram. Tell me what to do. We'll draw that free body diagram corresponding to what you just saw. Okay, so I'm gonna make my little dot maybe, huh? Okay, so I've got an arrow. Suggestion is I've got an arrow going that way. What do I probably label that one? Okay, F sub T, maybe we'll say F for the tension.
Could you do SB because it's like a spring?
Okay, yeah, we could.
I'm just curious. Like,
No, we could, yeah. That's fine. We could also probably do that, yeah, for a spring. Either way, the spring, a lot of times, we could. A lot of times people use a spring force when you're talking about harmonic motion and something's going up and down. But it'd be fine. I mean, not always. It would be fine. What else? Oh, okay, so another arrow going in that way. Okay, tell me when to stop with my body of the arrow. Okay, so don't go any further maybe? That's good. How come?
Does it move so the tension is bigger?
So the force due to the tension in the spring or tension in the scale must be greater than the frictional force because it did accelerate. Okay, interesting. Okay, so this is, from that list, how do we label a frictional force?
F sub F.
F sub F. Subscript F. A lot of times in other books, like in every book I've ever used, friction has always been just written like that, just as a script F. So you might see that. When you see a script F and the context is where you're talking about forces, that means friction, okay? So good? Okay. What do we notice here compared to on the first one? Well, you've already mentioned it, right? These forces, do they cancel? No, they don't. So if I were to consolidate those into a single force, if I added them up tip to tail, I'd end up with a resultant that looks maybe like that, right? What do I call that? The net force, exactly. Okay, there's a net force. And because there's a net force, there was an acceleration, right? Okay, good. All right, so Are there anybody can think of anything else maybe we could add to that? I think that's pretty good. I mean, it tells the whole story, or most of the story, the important parts of the story. Anything else going on? Okay, yeah, gravity was acting, wasn't it? Good, so this object, the combination of the friction block and the mass sitting on top of it, there has a weight, doesn't it? So the weight is acting in which direction? Down. Towards what?
The ground,
Ground, sure.
the table, oh no, the board.
Where's it, you're right, where's it really going? Where's it really going? Center of the earth, yeah, there you go, okay. Okay, is that it? Okay, if that were it, would my resultant point horizontally to the right? If I added all those vectors up tip to tail, it would also be kind of going down a little bit, wouldn't it? That thing didn't accelerate down, it accelerated straight and horizontal, right? Oh, yeah, what's the table doing?
Pushing up.
Pushing up. Yeah, you know what we call that? What we call that?
Normal.
The normal force, yeah. Normal force is our word in physics for a surface force, a force that's being applied by a surface to something, right? So, that's the normal force. The reason it's called the normal force, those of you in calculus, we've mentioned this word before, right? You've done some problems where you calculate a tangent line or a normal line. What did the normal line do? Tangent line was always parallel to the surface. What did the normal line do? Remember? So if this was our function, right, and we want to calculate the tangent right there, well, that's the tangent line, right, at that point of tangency. What's the normal line do? It's perpendicular. It's perpendicular to the function there. It's at a right angle to the tangent line. So what normal means, that's it. Normal means it's perpendicular to a function, or if it's three-dimensional, it's perpendicular to a surface. So the normal force, what do you suppose, in what direction does it always act? Well, up in this case, because the table is horizontal, right? But the normal force always acts perpendicularly to the surface that's applying it. So that's why it's called a normal force, if you're wondering. You know, we'll talk more about that next chapter, but that's what it is. Now, these two forces do what? Yeah, they cancel. The vertical components cancel, don't they? So really, did we need them? Well, you know, probably not so much. But next chapter we will. When we want to include all the forces in a free body diagram, that's how we want to draw it instead. Okay, I'm going to change this a little bit. I'm going to flip over this friction block, and I'm going to pull with the same 100 newtons of force. I think this is the right amount. I'm going to get it going here first. What do you notice about it now? Say it again. Is it accelerating? Didn't seem to be, did it? Once I kind of, I have to cheat a little bit to get it going. Once I kind of get it going, well, the same speed, isn't it? Okay. How does that change my free body diagram?
The friction force arrow is longer.
Okay, did anything else change? The spring scale, I'll tell you, the spring scale was on the same reading during both trials. So did anything else change? No, it didn't. Only thing that happened was the frictional force got longer. Tell me when to stop. About there, ish? About the same length?
It still went forward.
Okay, but it still went forward, right?
So it's just like a little.
But no, but I'll tell you, if I did it properly, they would be exactly the same length. Strange, it still went forward. What's the net force? 0. Okay, so let's think about this in the context of Newton's first law, the game show law. Right, the one that everybody, comes up on game shows all the time. Everybody's heard this before, can repeat it. An object at rest remains at rest, and an object in straight line motion
Remains in motion.
remains in straight line motion, constant speed, right? Unless acted on by an external force, AKA a net force, right? So the example of the three examples that we looked at, example one was the bucket hanging, we just talked about, the bucket hanging at rest from a rope. Example two was the smooth friction block that accelerated. Example three was the rough friction block that moved at constant speed. Remember that? Remember on Sesame Street, I think it was, they always put three objects up and then can you guess which thing is not like the other? Remember that thing? Remember that thing? And you had to pick which one didn't belong, right? Which one didn't belong out of that group. So of those three examples, I would say that two of them are very similar and one of them does not belong. Let's take a vote here. How many people think that the bucket does not belong? Nobody. How many people think that the smooth friction block does not belong? Okay. How many people think that the rough friction block does not belong? Oh, we got one vote. Nobody voted. What do you think? Which one? Well, I don't make you vote then. Let's just discuss it. What do you think? Which one is different? Something's different about one of those. I mean, sure, you might say that there's something that's different about each of them, but there's something important that's different about one of those.
Well, the smooth one is the one with the net forces.
The smooth friction block is the only one that had a net force that was something other than zero, right? A non-zero net force. And it accelerated, didn't it? So you're right. That's the one that doesn't belong. It's the one that doesn't belong. If I were to draw the net force up here, it'd be a pretty boring picture. It's just a point with no vector, right? Okay, so why is it that one of them's moving and one of them's not? Wasn't that what the law of inertia says? An object at rest stays at rest, aka the bucket. An object in straight line motion at constant speed stays in straight line motion at constant speed, right? Like it's doing, unless acted on by an external force, a net force. Well, there was no net force acting on this, so did it change its motion? No, right? So does that make sense? They're really the same thing? Does it still seem kind of fundamentally different that one of them was at rest?
Can you explain that again?
Sure. So this object right here now, right, when I'm pulling on this with my force, is it changing its motion? Isn't it constant speed, straight line, aka constant velocity? Right? Does that make sense? Whereas if I flip this guy over, it accelerates, right? Okay, right? So that one doesn't fit with the other two. Does it still seem a little bit though, like there's something different there, like the one at rest was fundamentally different? Does that make sense? Lexus didn't like that. One of them was at rest, one of them wasn't. Are you at rest right now? Yes? Okay. I'll buy that, but I'd also buy that you're not. It kind of just depends. I'm not saying it really does depend. We're at about roughly 45 degrees latitude, right? What's our Earth doing? Spinning on its axis. So at the equator, you're actually traveling around a point at the center of the Earth, relative to the center of the Earth, at about 900 miles an hour. So that's pretty fast. So we're going to be something more like, 700-ish, a little less maybe. Going pretty fast though. That's not a rest. Our planet is simultaneously moving around the sun at much higher speed, thousands of miles an hour. And our solar system, in which our planet sits, our sun sits, is embedded in the outer spiral arm of just a pretty normal spiral galaxy, but it's moving around the center of that spiral galaxy at a really fast pace. I mean, I'm going to estimate something like, 30,000 miles a second, something like that. Fast, right? So are we at rest? Not really. It's just convenient for us to think of ourselves as being at rest. Probably what we really mean though is maybe at rest relative to what? the chair, the floor, the ground, something like that, right? And that's a pretty convenient way to describe it, but still it's an arbitrary term. If you were sitting on a train, let's say you were on a train that you had like a sleeping cabin on the train, and the train was on a flat, level piece of track, let's say. You could hear the engine just kind of purring away, and you wake up, it's nighttime, shades are drawn, you turn on your little lamp, and you put a ball bearing or a marble on your flat table in the train, and it doesn't go anywhere. What's that tell you? Okay, it's moving along at constant velocity, right? And we know that because what if the train put on the brakes? What would happen to the marble? Okay, so it'd fall off the, you move forward off the table. What if the train went around a corner? What would the marble do? Slide off the side of the table, agreed? You can all kind of visualize that, right? What if the train were to speed up real fast, accelerate? What would the marble do? Kind of slide backwards off the table, but it's not doing none of those things, right? So it must be traveling at constant velocity. You can hear the engines rumbling, so you, why couldn't it just be idling on the track somewhere? Couldn't it be? Could you tell a difference? You couldn't, could you? No, you couldn't tell a difference. Are you at rest when you're on the train? Sure, relative to the train, right? We could say you're at rest. Is the train at rest or not? Well, we don't know until we look out the window, right? We can't tell. There's not enough information for us to tell. Does that make sense? So it's really, it's just a matter of perspective. I mean, you could even say, and I don't know if I recommend this, but you could say if you get stopped by a police officer, you're gonna give you a speeding ticket, and you could maybe say, well, why are you giving me the ticket? Well, you're exceeding the speed limit. You say, well, what speed limit? He says, right there, look at the sign right there, 65 miles an hour. And you could respond, well, that's not very specific. It doesn't say 65 miles an hour with respect to something in particular, right? So that's sort of ambiguous. It didn't specify that. Maybe it means 65 miles an hour with respect to the car in front of you, right? I mean, who knows? So, it's really, I mean, probably, I don't know if I'd advise that. Maybe it's strongly implied that it's 65 miles an hour with respect to the road. Probably strongly implied, but not stated. There is no fine print on that sign, right? So, once again, don't know if I recommend that. But it's all relative, isn't it? Motion's all relative. Okay, so looking forward then, what do we call this situation and that situation? Can you think of a word that might describe that? This is stationary. Maybe, maybe not. This could also describe that same bucket being pulled up at constant speed or being dropped down at constant speed. They could all be the same, right? The picture would be the same in all cases, I should say. Same thing with that, right? That could mean that this thing is, maybe it's got a lot of friction, like if I put, now if I pull on this same friction block with 100 newtons, I am right now, not going anywhere, right? That same picture could represent that. I guess maybe I'd have to make these forces a little bigger, right? What do we call that though? All those cases, what is it? Any have a suggestion? Say it again. Equilibrium. Equilibrium. Yeah, I was talking at the same time you were. I couldn't hear what you're saying. That's right. It's equilibrium. Okay, you've talked about that maybe in chemistry with respect to a reaction or something, right? Now we're talking about it with respect to forces. If all the forces cancel, so the net force is zero, we call that equilibrium, right? A couple things. Let's look at another example here. How about this one? Let's say I'm gonna throw a football. So if I'm gonna throw a football down the field, let's look at two moments in time when I'm throwing the football. Let's look at one example right as the football's about to leave my hand, okay? What would that free body diagram maybe look like? And let's go ahead and just ignore any friction, ignore any air resistance or anything, right? what might that free body diagram look like?
Like throw it like that.
Right as it's in my hand, just as I'm about to release it. What do you think? What do you think, Sean? The force is acting on it? Okay, so the free body diagram, all I'm looking for here, there's the football. I just want to know what vectors do I attach to that? So can you think of, Sean, what's one force give me a force that's acting on the football? Gravity is, sure, it's got weight, right? So one force that's acting on it is its own weight, the force of gravity. Now, what else? What do you think? What do you think?
Thrust.
Okay, whatever we want to call the throwing force, right? Whether you're going to call it a normal force or a throwing force or whatever. Let's call it a normal force because my hand is pushing on the football, right? And that's going to be, maybe I'm throwing it downfield, so maybe that force is up at an angle like that. That's it, right? Okay. Now, that's a little more complicated situation because those forces aren't acting along the same line. So that's kind of a next chapter type of a problem. What about after the football leaves my hand, it's going through the air? How's that going to change it? What do you think? Nicole, you got an idea? What do you think? Is it going to be the same? Not going to be the same. How many forces, if we ignore, we're going to ignore air resistance, ignore friction. So how many forces are going to be acting on it once it leaves my hand? How many? No forces? Oh, just gravity. Okay. Yeah, that's it. When it leaves my hand, the only force acting, that one goes away. That was the force that was acting from my hand. So once it leaves my hand, the only force acting is gravity, right? What if this were in outer space where there were no gravity? After it left my hand, what would be the force acting on the football? Nothing. Just going to travel in the same direction at the same speed forever until it encounters something that provides a force to act on it, right? Okay? So that's kind of a misconception I think people have sometimes, is that when you launch a projectile, the force used to launch it somehow is attached to that object even after it's already left, right? Whether it's a football or a bullet or a catapult throwing something or who knows. Not the case, right? Once it leaves whatever the object is that's throwing it, the only force acting on it is gravity. It's technically in free fall. And we'll talk more about that next chapter. What about this situation? If an object, let's say a car, is traveling down a straight stretch of road at constant speed, okay, what can you tell me? Is the car burning gas? If it's just traveling down, if it's traveling down this stretch of road, level stretch of road, let's say we're going to ignore any air resistance. Is it burning gas when it's doing that? Yeah, it is, isn't it? Is it burning more gas than it would if it were idling in a parking lot? I'll tell you, yeah, it would be. It would be burning more gas. So the engine's doing some work, isn't it? Right? Is a force required to act on the object to keep it moving in a straight line like that? Okay. And if you nod your head, yeah, I could buy that, because really what you're talking about is the driving force, aren't you? Agree? Why do we need the car? Why does it need to provide a force? Apply a force. Okay, why? What would cause it to stop or slow down? Friction. Okay, yeah, sure. And lots of friction. Let's think about different kinds of friction acting on the car. What would they be? Okay, there's rolling friction for sure. Yeah, there's going to be rolling friction with the ground. Okay, what else? Air resistance. Yeah, that's probably the biggest one, is air resistance, honestly. Air resistance is just fluid friction. And it's very real. Put your hand out the window of the car when you're driving real fast and your hand gets pulled back, doesn't it? Why is it getting pulled back? Because all the little air molecules are rubbing against your hand, right? So that's a real one. And then there's probably some internal friction inside the engine itself, you know, in the axles and the drive shaft and things like that, right? So yeah, definitely the car has to provide some force to overcome friction. Let me ask you this question in a slightly different way. Is a force required to keep an object moving at constant velocity? Now what's implied there maybe is a net force. Is it? Is it? It's moving at constant velocity. Is there a, is it accelerating? No. So if there's no acceleration, is there any net force? There's not. There's not, is there? Right? So when the car is moving down the road with its cruise control on, the net force is zero, right? If the person taps on the brake and disengages the cruise control, what do you notice happen to the car? It slows down. Is there a force acting on the car then? What do you think? It starts to slow down. Slow down in physics terminology means what? Okay, decelerate. We kind of don't like that word, but so it's got maybe negative acceleration, right? Or decel. Well, I'll grant deceleration, right? So there's some acceleration acting there, isn't there? Right? So if there's acceleration acting, then there must be a net force. There is. The net force is due to the friction. As soon as you remove the driving force of the car that's counteracting the friction, now the net force is no longer zero, is it? Right? Now it does have a net force, which we can observe because it's decelerating. Make sense? So you got to be careful with this one. People sometimes kind of blithely state that a force is needed to keep an object moving. Not true. A force is not needed. A net force is not needed to keep an object moving. Maybe you need to provide a driving force to counteract a different force, right? But that's not what, that's to keep the object moving, the net force can be zero, right? Is inertia a force? Sometimes we throw words around, we're not careful about it. Is inertia a force? Not really, is it? It's not like tension or friction or a normal force or a gravitational force. Inertia is something different. Inertia is just kind of it's kind of a concept, really. If we talk about an object's inertia, what are we probably, let me ask you this, what has more inertia, a dump truck or a bicycle? A dump truck does, absolutely. And why is that? Okay, yeah, and mass is, but without using the word mass. It's got more matter, good. How could you prove it to somebody? Say, here, I'll show you. That dump truck, I'll prove it to you right now, that dump truck has more inertia. Go push it, yeah. Go push the dump truck and not much is going to happen. Go push the bicycle and something will happen, right? So what is really inertia then? Inertia really is just the resistance an object has to changes in its motion. Agreed? Now we have a name, we have a way to quantify that, and that's mass, right? Before we leave though, here's what I kind of want to leave you with. There's the last thing. We got to divorce these ideas in our mind of mass and weight. Are they the same thing? Not at all. Not at all. We use them pretty interchangeably. If you go to the weight room and you lift weights, if you lift weights in Canada or Europe, you're going to go put a 22 kilogram plate on, on the standard. You're going to do bench press or something, or squats. What's the equivalent if you're in the United States? It's printed different. What's it say? Yeah, it says 45 pounds, right? They're interchangeable, aren't they? I mean, you're lifting the same amount. If you put on a 22 kilogram plate in Canada or a 45 pound plate in the United States, we're lifting the same amount. So they must be the same. Well, we use them kind of in the same way, but they're not the same. They're not the same at all. Is mass a scalar or a vector? It's a scalar, right? It's a scalar. All that mass is required to define a mass is a number, right? What about weight? It's a force. It's a vector. It's a vector. When we say a 45-pound force, that 45-pound force is being applied in a specific direction towards the center of the earth. And you're using your muscles to counteract that, pushing away from the center of the earth, right? They're different things. Why can we use those somewhat interchangeably on the surface of the earth? Well, does the acceleration of gravity vary very much on the surface of the earth? Okay, not very much, right? Very microscopically, but nothing very noticeable. Now, if we were to go put that 22 kilogram plate, if we were working out on the moon, we'd be able to do a lot more reps with that 22 kilogram plate than we can on the surface of the earth, because the weight would be different, right? It's still 22 kilograms that we're lifting, but the weight would be 1/6 what it is on earth, right? Does that make sense? Okay, so what is it then when you find your, what would be, if you're an astronaut, what would be a pretty simple weight loss plan?
Good.
Yeah, go to the moon, right? That's a pretty easy way to change your weight, isn't it? Right? It's be a little more challenging to have a mass loss plan, right? Because then you really probably have to do some exercise at night, right? That's different. That's a little harder to do. But weight is really a little different, isn't it? When you are measuring your weight, what do you typically do? Stand on a scale, right? Is the scale measuring your weight? What's it really measuring? Is it measuring your weight? Okay, so it's measuring the force of gravity. Maybe, okay, we could call that weight. Well, I'm going to play a trick on you. Say you put that scale in an elevator, and the elevator begins to accelerate upward, and you look down at the scale. What do you think the scale is going to read? It's going to read a heavier weight, isn't it? Isn't it? And can everybody agree with that? That you can kind of feel that you push on the ground harder when the accelerator or when the elevator is starting to move up. What about when it gets to the top and it starts to decelerate upward? You feel a little bit lighter, right? Okay. Did your weight change? No, it didn't. So is the scale measuring weight? It's not. It's not measuring weight. It's measuring what we might call apparent weight, but what is it really? Let's draw a free body diagram and see. These things are actually kind of helpful. So if this is the scale, what are the two forces acting on it if I stand on it right now in the room? What do you think? Say it again. Gravity and the normal force, right? So my weight is pushing down on the scale, right? And the scale is pushing up on me with a support force called the normal force, right? When I'm at rest in this room, what's the net force? 0. Okay, but if I'm accelerating upward in the elevator, which one of those two forces has changed? No, my weight's not going to change. But the normal force is, right? In order to push me upwards, doesn't the elevator have to apply an extra force to me to accelerate me upward? So that means that this force is going to get a little bit bigger, and there's going to be a net resultant force causing me to accelerate, right? And so the scale, which is really measuring how hard I'm being pushed on by that apparatus, right? That's really what it's measuring, is the support force, right? Is going to seem to be a little bit higher. Agreed? Now, when I'm coming to rest, and the elevator then stops pushing as forcefully, so I can decelerate, right? I need to have some downward acceleration to slow me down, right? Then it's going to do this, right? Then it's going to go, it's going to shorten, and now I have a net downward force, and so the scale should read something less than my normal rest weight. Make sense? Okay, good, good. You guys are getting this, good. So I'll give you, like I said, I'll give you one day this week to kind of finish up, retake the test if you want to. I've got the labs are all graded. I want to go through those with you in class just a bit before we start on our next adventure. I'd like to do another lab here coming up. If we don't do it this week, kind of like at least start it this week and maybe work on it next week. But I want to give you a little feedback on those first, about some things that could be maybe tweaked a little bit for the next time we do a lab. But kind of get yourself mentally prepared for that. I'm gonna assign a couple. Here's kind of the way I'm gonna do this. And understand this isn't for your class, but for the other class, which is huge. I'm gonna probably kind of give you some book assignments, and so they'll have to be, the big class, I can't have them all doing a lab at the same time, so there'll be some days where half will be on and half will be kind of working on assignments, and then they'll flip-flop. You guys can do that however you want to. And we can all be on the same day if you want to, and then we can just be there less time. I don't care. But the lab, that's how the lab's gonna be structured over maybe, a longer period of time. So the other class, everybody can have a good chance in a small group to work on it. I'm thinking about, as I'm designing this lab, I'm thinking about asking you to do two different things. Maybe one lab that I've got set up, and I might have you design a lab too, to represent or to demonstrate something. Okay, so, I don't know, it'll be fun. Alrighty.